We'll briefly discuss how Newton method can be implemented efficiently, in particular when there is structure present in the problem. So if you recall, the Newton steps were given by xk plus 1 equal to xk minus eta times Hessian of f at xk inverse times gradient of f of xk. Now, although it is written as Hessian inverse times gradient, this quantity is not, in practice, it is not really calculated by first calculating the Hessian inverse and then multiplying it with the gradient. Instead, what we do is we solve. So in order to find this, we solve the equation, the system of linear equations, Hessian times u equal to gradient of f of xk. So this is a system of linear equations. We solve it for u, and that is our step direction, right? So in reality, we are always solving this equation instead of first finding the inverse and then multiplying. The reason for that is that finding the inverse takes a little bit more complexity as compared to solving this equation. Solving this equation is faster. And then what does it mean for something to be faster? That also we will discuss. So let us discuss this problem of solving a system of linear equations, right? Same way as in Newton, we need to solve a system of linear equations. So let's see how do we solve it and what are the issues surrounding it. First of all, we need to measure complexity of any mathematical operation. How do we do that? How do we measure the complexity of solving some linear algebraic problem? So we can measure the complexity by using the notion of flops. Flops means floating point operations per second. So this flops is a terminology that is coming from the computers. In computers, a floating point operation is something like addition and multiplication. All other operations are carried out in terms of addition and multiplication, and the power of a CPU, for example, could be defined as the number of floating point operations it can carry out per second, and therefore the complexity of such an operation or any operation can also be measured in those terms. How many floating point operations are actually required to do a certain operation, right? And if we can figure out for an algorithm or an operation that the number of floating point measures, suppose that we can roughly measure it as, so suppose we have a rough measure that n flops of n is the requirement, then we can say that order of flops of n, right? Order of flops of n means some constant times flops of n is the flops requirement or floating point operations requirement, and we can compare various algorithms on this basis. I mean, by itself, flops is not very useful because it is highly implementation dependent. But if there are multiple algorithms implemented in a similar way, they may have a similar flop count, right? So this is a flop count. Note that we are ignoring here in this, when we say this, that this is the order, we are ignoring lower order terms. First of all, so if, for example, if we say that it is order n cube, flops is n cube, so then we ignore n square and n terms, then it is largely machine independent, because it does not matter if I have a fast CPU or a slow CPU, because I am just giving you the flop count. You know, it depends, whatever CPU you can arrange, you can do that operation. And this measure of an algorithm in terms of flop count, it does not depend on the machine. But it is, at the same time, it is not very accurate. The reason for that is that a lot of optimization inside a compiler is also done on top for any algorithm, and that optimization may sometimes reduce the flop count by a lot, right? So it's not very accurate measure, it is a rough measure only. Okay, so now let's look at the flop count of various operations. So let's first look at some basic operations just to get an idea of what really is meant by a flop count. So let's say we are calculating x transpose y. X and y are two vectors in Rn. So x and y are two vectors in Rn, and we want to calculate x transpose y. How many operations are required? You can easily see here that I have to multiply xi with yi, and right, so those are n multiplications, and then I have to add all of them. So let's say n minus 1 additions, but approximately if I bound it by a constant, I could say that this is order n flops. Right, actually it is 2n minus 1, but I am approximately saying 2n minus 1 is order n, some constant times n, right, ignoring the minus 1. Then second is, suppose that I have to do matrix vector multiplication. How many flops would that take? You can see that you would have to multiply each row of this matrix with x, right? So that each row would take order n flops, and then there are n rows. Let's say that there are n rows, then the requirement would be order n square flops. Okay, so vector matrix multiplication takes up order n square flops, right? So these are the requirements, but even in these basic operations, we can actually utilize the structure, and if we do that, we can speed up our calculations significantly. An example of a structure appearing in a vector is that it could be sparse. So if x, vector x in Rn is k sparse, right? If it is k sparse, or it has k non-zero entries, then what we can do, how can we calculate x transpose y faster? Recall that x transpose y is nothing but summation of xi yi, and then when we are carrying out this summation, we may just not consider the indices of I where x is 0. So those indices we can just throw away. We can only consider those indices and carry out the multiplication only for those indices, because we don't need to really multiply anything by 0. We already know that it is going to be 0. So really the requirement here is 2k minus 1 operations. So I could say order k operations, and if k is much less than n, then order k could be less than order n, right? So for example, k could be much less, order of magnitude less. In that case, order k would be really significantly lower than order n. And likewise, if you have to calculate ax, same way, at each row you will require order k flops, and there are n rows, so order nk flops, right? So order nk flops, which could be significantly lower than order n square. Okay, so these are some basic operations that we have considered, and these are their flop counts depending on whether they are sparse or not. And similar ideas, lots of similar ideas are similarly applied to solving ax equal to b also similarly. Okay, so for example, when we talk about solving ax equal to b, a very simple case, so easy case, let's say easy case 1 is when a is diagonal. When a is diagonal, what can we do? Remember that if you have a diagonal matrix, it would be of the form a11, a22, and so on. All this will be 0 times x equal to b1, b2, all the way to bn. Now, inverting a diagonal matrix is straightforward, and in fact, xi is equal to bi divided by aii. So this solving ax equal to b for a diagonal matrix really involves calculating bi by aii, which is a single division. So one operation per entry. So order n flops. So solving ax equal to b for diagonal case is really easy. You just have to do order n operations. Another easy case is when A is lower triangular, right? It is not as easy as diagonal, but still it is easier than the general case, right? Actually, I forgot to mention, in the general case, the complexity of solving this is order n cube, right? So in the general case, it is order n cube, but oftentimes you can utilize the structure and then the complexity goes down. So in case of lower triangular matrix, it would look something like this. You have A11, then all zeros, then A12, A22, all zeros, and A13, A23, A33, right? So it would continue something like this. And you have X1, X2, X3, and so on. And this is equal to B1, B2, B3, and so on. Right? So this would be the lower triangular case. This is A. And how would we solve this? So basically there is an order in which we can solve, which would make it easy. First of all, observe that X1 equal to B1 by A11. That's clear. And then when we are solving for X2, we can use this value of X1. So X2 is actually equal to B2 minus A21 X1 divided by A22, right? So X2 is equal to this. And in the same way, we can calculate X3 using X1 and X2 values. So this is called back substitution, right? You calculate one, then you substitute its value in the other one, then you substitute both the values in the third one, and so on. Right, so let's count the flop count for this. So we are doing one operation here, 3 operations here, and similarly we are doing 5 operations, 7 operations, so on. So the flop count is something like this. So it goes like this till we reach 2n minus 1. So this is approximately order n square. Right, so this is the easy case 2, which is the lower triangular matrix. And for this case, the flop count is order n square. Okay, so is there a scenario where it could be less than order n square? So that could be case, for example, when the matrix is lower triangular, but it is also banded. So what does it mean? The matrix may look something like this. So it is lower triangular, which means everything here on the top is 0. And it is also banded, which means the only shaded part is non-zero. And in that case, what would happen is that when you start back substituting, you won't have to go beyond a certain point. You will just go all the way to k. So this complexity becomes actually order kn if it is banded by a k amount. Okay, so if it is banded and lower triangular, then you can recognize it and calculate it order kn. So actually what happens is that any solver, any efficient solver that you might have seen, like the ones that CVX uses internally, or those are used in Python, a lot of linear algebra libraries and so on. So they will all recognize this kind of structure. So they are pre-programmed to recognize this kind of structure and quickly make use of it. Right? So all of them will actually properly make use of all this structure and make sure that the implementation is such a way that it is fully tuned to the exact structure that is available. There are other easy cases also. So for example, another easy case is orthogonal matrix. So orthogonal matrix, A inverse is actually A transpose only. So orthogonal, if you can actually recognize that it is an orthogonal matrix, or you know in advance that it is an orthogonal matrix, then it is just an order n square operation to calculate its inverse. Another is the permutation matrix. So what is a permutation matrix? Matrix is one which permutes the entries. So for example, this is a permutation matrix, right? And because it permutes, it basically puts x2 in the place of x1 and x1 in place of x2. It interchanges first and second entries. And the P inverse is equally straightforward. It is the inverse permutation, right? So this is the inverse permutation. So calculating the inverse of a permutation matrix just amounts to exchanging things, and therefore it is really copying things from one place to another. It does not incur any flop count because there are no floating point operations, just copying. So in fact, in practice, the copying complexity or copying time will dominate, and there's no floating point operations, so there's no CPU time. You can think of it like that. Then we can have another case is factorization. So factorization is not really easy case, but more of a trick. So if you have a matrix which factorizes as A1, A2, and you have to solve AX equal to B, right? Suppose you have to solve AX equal to B, then you can solve it in two steps. So you can write it as A1, A2, X equal to B, and then you can first solve A1, U equal to B for U, right? So you can first solve this for U, and then in the next step you can solve A2x equal to U, right? So there are really two steps to solving for X. First solve A1U equal to B, and next solve A2x equal to B. This means that the complexity or flop count for each of these steps will get added instead of being multiplied. Okay, so if you can factorize such that A1, A2 are simple and their structure can be utilized for solving A1 U equal to B and A2 X equal to U, then you just have to add their flops and that's it, right? So for example is Cholesky factorization. If you remember, Cholesky factorization was A equal to L transpose. So suppose that you can factorize, or you know the factorization of Cholesky factorization, then you need to solve L transpose X equal to B. And to do that, first you can solve L times L transpose X equal to B for L transpose X, which would require how many flops? It would require, because it's a lower triangular matrix, so it is requiring order n square flops. And then the next step would also require order n square flops, so total is also order n square. Right? So total only order n square flops are required whenever you can carry out the Cholesky factorization, while otherwise you would have required order n cube flops, right? And another example of this is LU decomposition. So LU decomposition is generally applicable to any matrix, and it is basically PLU, right? The factorization is P times L times U. So what does that mean? Here P is a permutation matrix, and then L is lower triangular, and U is upper triangular. So solving the upper triangular and lower triangular are simple. They are order n square. Permutation did not take up any flops. So overall complexity is again order n square flops. Note that here carrying out the factorization may not be easy, right? So carrying out the factorization may take order n cube time, right? So it is, I'm not saying that generally you can just do factorization and solve it faster. Carrying out the factorization may also take order n cube time, which means that either you should know the factorization or you carry out the factorization once and solve many equations using that. That is sometimes the case, that you have to solve many equations, systems of equations with the same factorization. So that could be the case, or this step could be faster. So this step could be faster when A is sparse or banded, right, and so on. So if A has some special structure, again there are many algorithms to properly factorize these matrices, right? So just to summarize, we have seen many basically efficient ways in which the calculation of AX equal to B or solving AX equal to B is possible, and all these methods enable us to implement the Newton method in an efficient manner. And the idea basically is that in general, solving ax equal to b, so in general case it takes n cube, but the idea is that it could take n square in special cases, right? In most of the special cases it actually took n square, so it is worthwhile to invest in trying to find the structure so that we can actually reduce the complexity and get the order n square complexity that we require, and then that basically allows us to implement Newton method for much larger systems. So in the general case you may have n at most 1000, you don't really go beyond that for the general case, but if you have special structure you could go to 10,000 or even 100,000, right? So if you have special structure, then it can be sometimes utilized to implement Newton method for very large scale problems also, or I would not call it very large scale, I would call it moderately sized problems rather than small problems.